Hello everyone, good morning. Welcome to the class ECE451 Control Engineering. Today we will keep working on the matrix form of the systems. Last time we have discussed we have different way to describe a system in matrix form. Okay, so we keep working on that. This is the ECE451. This lectures for the 10th week, Monday's class. Okay, we have several forms of the matrix equations for a system. Suppose we have this, like we have a system with transfer function T of S, which is a fraction. I write this in two parts. The first part is it is a primer fraction. Numerator has lower order than denominator. Okay, suppose denominator has order n. This s to the n, then coefficient I use a1. This is adds to the n minus 1 plus more terms until a to the n minus 1. Here will be s to the power is n minus 1, should be 1. And the next will be a n times s to the 0, it is just 1. Okay, so this is denominator. Numerator, we suppose it is some coefficient b1 s to the n minus 1 plus b2 s to the n minus 2 until some b n minus 1s plus bn. So this is a proper primer fraction. The fraction has order lower than the denominator, right? The numerator has lower order than the denominator. And suppose we have a constant d here. Then we have the CCF of the system. We have four matrices where a C means the controllable canonical form. Okay, this matrix contains three parts. The top row, top row, it is just coming from the denominator of the transfer function. That is a negative a1. Here's a1, then here's a negative a1. The negative a2 until negative an. We put these coefficients a1 to an here with a change of the sign. And this column, it is 0. This part, it is a unit matrix with lower size. This is n by n. Then this will be n minus 1 by n minus 1. So this is AC. And the B for the CCF controllable form, it is a matrix. The first is a vector. The first element is 1. Then all the rest values, they are 0. Alright. And BC, CC, CC. Okay, this C means the matrix C, and this C means the controllable canonical form. This will be B1. It's just these coefficients, B1, B2 until Bn. And the D, it is just this number D. So we have CCF will be this one. And we also have OCF. OCF, I put it together. AO, BO, CO, and the DO. What it is? I put them all together. These form a square matrix, right? AO, it is n by n, and this is one column. B is one column. C is one row, and this is one number. So the totally is n plus 1 times n plus 1, right? One more size than A. And this one equal to, I put AC, BC, D, CC, CC, and DC. I put this together. This is also matrix. I do the transpose. So the OCF just transpose. So CO will be 1 0 0 0, but in a row, and the BO will be this B1 to Bn. Okay. D is still D, and AO will be a transpose of AC. Right? AO is just transpose of AC, and the system in matrix form. There will be X derivative equal to that A times X plus B times U, and Y equal to CX plus DU. Here U is the input, Y is output, and X is the state variables. So we have this. Alright, so when you know the transfer function, similar if you have the equation, differential equation of a system, then you can write the system in matrix form with in the CCF or OCF. You can have this one. Alright, and we have another one. That is a MCF, the modular canonic form. Modular canonic form. You need to perform the partial fraction of TS, and rewrite it as a summation of several fractions. Each fraction you can use either CCF or OCF. Then you have a small part of the MCF, and combine each part together. You have the MCF, right? I don't write it here. You should know how to do. And I have homework, so try to practice on homework. You should know what that is. Actually, this is not unique. MCF is not unique. There should be different way to realize it. Yeah. Okay. And here, actually, we have more information. We can think this by a reverse way. If we know a system in this way, suppose we already know this way, can we find the transfer function? Right. So far we work like this way. We have the transfer function, then we have the matrix form. Now if we already have the matrix form, can we find the transfer function? Well, for CCF or OCF, well, we will say yes, and that's quite simple. You just put the right number in right place, that will be fine. Like suppose you have the CCF, you have this 4 matrix, then the transfer function it is just this one. You put this A1 to AN here, and put the B1 to BN in the numerator, and put D here. You have the transfer function. But we want to know more in generally, so we can think like this. Suppose we have, now this is the problem different with here. Here's a kind of review. Now we suppose we have this system. We have the system in this way. Alright, we have the system in matrix form. Then we want to find the transfer function. How to do it? Actually, not just the transfer function. We want to think more. Suppose the input is given, what is the output, right? Okay, we use a Laplace transform, similar with the single equation case. So, how to solve it? That means we want to find y if u is given. Right? We want to do this. Okay, we perform Laplace transform. We will have, this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of s plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will be s x of s minus x of 0 equal to a x of 0 plus b u of s. And y, we will have this is x, right? Take one derivative. So this will equal to C x of s plus d u of s. We have these. It looks like almost the same as the single function case, but now they are not single function. X order is x, they are vectors, and u and y, they might be also vectors. Alright, so here what is the meaning of that? We can see like this. X dot, we perform Laplace transform. It is Laplace transform of x1 of t, take derivative until xn to the t of t, take derivative, perform Laplace transform. Then we have the Laplace transform of each. So this is a s times x1 of s minus x1 of 0 until xn of s minus xn of 0. We have this. Okay, this is a vector, and this vector we can write it as s times x1 of s until xn of s minus lowercase x1 of 0 until lowercase xn of 0. Right? Okay, this is what? This is just the s times x of s minus x of 0. So you see the first vector, this vector is just capital X of s, and this vector is just lowercase x at time 0. But this capital X, these two x, this capital X and this lowercase x, these two, they are vectors. They are vectors. Alright. So in the matrix form, you will see when you look at a variable, state variable x, if it is just x, you know that it will be a vector. If it is x with I here, with a 1 or n here, that means it is an element of x. It is a single signal. This is signal. And this one just x, that is a vector. And capital X is also a vector. This is capital X is in S domain. Alright. So you see, this x dot, we perform Laplace transform on it. We will have Sx minus x0. The meaning is different, but the formula looks exactly as same as the single function case. Alright. Okay, now we have this one. Yeah, this one I explained. For the rest part, they are just a normal calculation, because nothing special, just perform Laplace transform, right? So x tend to be xs. Alright, then we want to solve x from here. We rewrite it. This capital X and the capital Y, they are unknown, and u are given, right? U are given. This is input. Suppose you know input, otherwise you cannot know what is output, right? Depending on the input. And x, y, they are unknown. So we want to solve this. We want to solve these two. Okay, I move unknown to one side. So we have these two equations. The first one. Okay, just the first one. First one, it is s times capital X s minus a times capital X of s, and equal to, I move x0 here, and plus v times u of s. And we have this one. Okay, so this part, the first part, I can write it as s minus a times x of s equal to x of 0. Yeah, I don't need this. Plus b u of s. Am I good? Not exactly. You know, A is a matrix and S just one element. So the size of these two, they are not matched. We need to make some change. I write these x of s times s equal to s times the unit matrix times x of s. Then here I put s times the unit matrix, right? Now both I and A, they are same size, n by n, n by n. As I, A, they have same size. Same size. We have this one, and I is this one. Which you know what is I? I is 1, 0, 0, 0, and only this line, the diagonal values, they are 1. All the rest, they are zeros, right? So this is a unit matrix. All right. From this one, now we can solve x of s. I just divided this part to the right side. But remember, they are matrix, so when you calculate, you cannot change the order. So you have to work this time s minus sa minus a on the inverse on the left side of both. On the left, okay, just time this on the left of both sides of the equation. So I times this one here, then this one inverse and times on it, so they cancel, right? I only have x of s. The other side is si minus a inverse times x of 0 plus si minus a inverse times b times u of s. Alright, this is x. Then we plug in, we can have y. Y is c of x plus d times u. Now c times x plus d times u. And x is here, so it is a c times si minus a inverse times x of 0 plus c si minus a inverse b u s plus d times u of s. So we have this. We have this one and this one. We have these two formulas. One is for the state variables, the other is for the output y. Both are formulas in the s domain. Then we can have the similar formula in time domain. We by the inverse Laplace transform. The first one, okay, we use a notation, denote si minus a inverse as capital phi of t. Okay, yeah, maybe I need a lowercase. This one called for capital. It's fine. Okay, denote this one inverse Laplace transform of this one as phi of t. Okay, then we have x of t will be here there will be phi of t times x of 0, right? And second one will be here we have two functions times together, right? The first part I have s, second part I also have s. So this is a multiplication in s domain. So we go back to time domain, there will be a convolution, right? So but b here, you can think b is a part of u or b is a part of the first part. So it will be phi t times b convolution with u of t, or phi t convolution with b times u of t. Yeah, both works. Alright, this is for x. And for y, we have similar thing. It is this one, we go to time domain, then we have c times phi t times x of 0, right? This is the first term, and plus this is a c phi of t times b convolution with u of t, sorry, the time domain, u of t. So we have these. We have these two formulas. We have these two formulas. Here you should know phi of t. Actually, it is a matrix, right? You see, this is a inverse matrix. It's n by n, so this is still n by n. N by n, then perform inverse Laplace transform, go to time domain. So phi t is also n by n. It's n by n matrix. Right. It's a matrix. Phi t is a matrix. So phi t is a matrix. Then the convolution, if I use phi t convolution with bu, you need to calculate for every element in phi t with the convolution with b times ut. So that's a lot. And use the first way, phi t at times b firstly, before I do the convolution. This one, it is a square matrix, and b is a column. You times these two together, your result will be a column. Result will be column, right? When you do the multiplication of matrix with a vector, the result is also a vector. So you times phi with b firstly before you do the convolution. Then in convolution, you need to perform with every element in this column, right? So you don't need to perform matrix. If you use the second way, phi t is a matrix, then you need to consider every element in this matrix, do convolution with the next one. There will be more, right? If like n, the second, this part, if you calculate by this part, you need n times n squared calculations. The other one just the n calculations. Similar for y. This part you can also write as or c times phi of t convolution with b times u of t. You can also consider this part as this one. But this one, this is a matrix, this is a square matrix, this is a row vector, and this is a column vector times function. So the result, this one gives row vector times a square matrix, result is a row vector. And this time together, this is a column vector. Then you need a convolution of this one with this one. Right. And if you calculate by this way, there will be a c is a row vector, phi is a square matrix, b is a column vector. This one will give you result just a single function, single element. Then convolution with u. U is also a single function. So you only need one convolution. Right. So I write the formula, I use this one. Use this one. This one also work, but more calculation. This one also work, but you need more calculation. So I prefer use this one or this one. Okay, so now we know how to find the output from input, if input is given. And also we need an initial condition x of 0. Then you can have output, right? You can have output. And at the same time, actually, we have the transfer function. What is transfer function? Is here, right? Y in S domain. So we y over u give us transfer function. In case initial is 0. Initial is 0. Okay. So the transfer function is y of S over u of S, which is this part over u, right? So it is a c times si minus a inverse b plus d. So this is transfer function. We can have the transfer function based on the matrix. If we have system look like in this way, then we can have the transfer function use this formula. Use this formula. All right. Okay. So this is about the transfer function, and at the same time we also have the formula to solve the system. Right. We have these two. We have these two. We can solve the system. When input is given, we can find output, as well as the state variables. Right. Okay. So this is one thing, and at the same time we have another problem. we have CCF, we have OCF. Then if we know the transfer function or we know the differential equation of the system, we can find the CCF, OCF, or MCF. Now suppose we already have the we already have the matrix form, but it is not in the canonical form. Then can we change it to be a canonical form? So this one is we call it the transforms of the matrix state equations. Yeah, we can have some change. Okay, the first change, actually this is just a change on time. First change on the time. This will not change to like you start with matrix equations. By this way you cannot have the canonic form. But this is also kind of transform, so I put it here. A transform. The first one we change it to let me see. We call this is in the time we change. It's a time changing, time scaling. Time scaling. Suppose I have x dot equal to ax plus bu and y equal to cx plus du. Actually here all these x, y, u, lowercase y, they are functions of time t. Now we can let we use t, we use different t. I say tau equal to some alpha times t. So alpha is kind of scale, alpha of t. Then we can have what? We can have this, the dx over dt. Right, this is derivative of x. This is function of x. It will equal to dx over d tau times d tau over dt, right? So d tau over dt is alpha. This is alpha times dx over d tau. Alright, we just plug in. So we have alpha times dx over d tau equal to a times x. But now is t is replaced by tau over alpha. So actually this is tau over alpha plus b. U is also t replaced by tau over alpha. And y will be cx tau over alpha. This is also tau over alpha plus b times d times u of tau over alpha. Now we have this one. So you see this is a new equation. I move alpha to this side. Okay. So we have new equation. New equation will look like this. Yeah, put 1 over alpha. Right? 1 over alpha. So 1 over alpha times a is 1 over alpha times b. And c and d, they are same. C and d are the same. And x and y, they are also not exactly same with the original one. The time variables are different. Okay, so this is time scaling. And the second thing we call the amplitude scaling. Amplitude scaling. Amplitude scaling, we use we have xy, right? So x1. So x1, x2 to xn. We want this is, I say this is some lambda. Okay, lambda 1 x1, lambda 2 x2 to lambda n xn. We change x by this way. Okay, these are some new x. I see this hat. I put the hat here. new variables x1 hat to xn hat, or maybe I can use z. Okay, anyway, x hat. I replace x by this part, then original system will change. So we will have lambda 1 x1 hat derivative, right, and lambda 2 x2 hat derivative until lambda n times x hat n derivative. This will be x derivative. Now change to be this one, and equal to a is still a. I put a here, right? A is a constant, contain a constant, but x, now x is a still like this: lambda 1 x1 hat, lambda 2 x2 hat until xn lambda n times xn hat. Okay. This is the ax column, and plus b times u. U will be similar thing. U are same. I just put u here. Yeah, u will be same. Input will be same. Then by this way, you see, if we want to go back to the standard form, we will have x1 hat derivative until xn hat derivative. We will suppose the left side will only contain this column. Then this one will equal to I divide by lambda 1, divide by lambda 2, divide by lambda n. In each row, I can write in a matrix form. This is a lambda 1 inverse 0, 0, and 0. Lambda 2 inverse, then 0. Right, here's a lambda n inverse. I write in this way. This part is 0, this part is 0. This one times a, right, I divided this one and put it here, times a times, okay, I can also write this as lambda 1 until lambda n. Here's a x1 hat to xn hat plus b, I write this as p, a p inverse. This will be p, right? This will be p. So before b, I also need a times p inverse on it. So this is p inverse times b times u of t. Yeah, I write it this way. And also for y should be c times x. But now x is, yeah, I can also write this in metric form. This is a lambda 1 to lambda n times x1 hat until xn hat. Okay. Writing this way. And writing this way, then here should be c times x. Now x is a this is a p. This is p inverse. P inverse. Yeah, I just use this as p. Sorry. Yeah, here's a p. Okay, here's a p. Then this will be p inverse. This is p. Okay, yeah, I'm good. This is c times p times x hat, and plus d times u. Nothing changing on u. Alright. Okay, so we have this. Y is this one, and for x will be x derivative will be a. Now a is a p inverse ap times x. This is with a hat. X with a hat. X hat take derivative. X hat. And plus b. B will be p inverse b times that u. And y will be c p x hat plus d times u. Alright. So we have a new system. Not exactly new system. Same system. For the same input, you will have same output. But the inside the state variables, you change them. You change those state variables, and then the equation looks different because the parameter matrix are changing. Different, right? Different matrix. D are same, but A, B, C they change. So we can have this one. All right, we call these as we can even have more generally, right? Here I think P is just this lambda 1 to lambda n, just this matrix, but actually we can have more general. So we call that is a similarity transform. This is 1, 2, 3. Similarity transform. Suppose we have system looks like this: x star equal to ax plus bu and y equal to cx plus du. We have this. We let x equal to some matrix P times x hat. Then we can have x hat derivative equal to that is the same way, just like this. Yeah, this part is same. If P is this, if this is P, that is amplitude transfer. Yeah, amplitude scale, right? Amplitude scale. Now we can have more generally. We can choose a P. P might be not look like this. We only need saying we want the inverse of P actually, right? So P should be determinant of P cannot be 0. Okay, we only need this condition. Then the new equation will be P inverse AP times x hat plus P inverse B times U of T, and y equal to Cp times x hat plus du. Now we have this. We will have this. Compared with the original one, the relation between input and output are same, but the state variables change. We use new variable for the state variable, and of course the matrix also change. All right. Now we want to find we will go back to our problem. We start from any matrix form system, any system in matrix form. We want to find the P, so that after we change x by this P to x hat, we have new equation. We want this new equation is CCF or OCF. Can we do that? We'll say yes. Okay. We'll see. Now we have a problem. For given system, x star equal to ax plus bu and y equal to cx plus du. For this one, we want to find the matrix P. The determinant of it is not 0, so that x star equal to x hat star, okay, and then this one, so that the similarity transform x of t change to be P times x hat of t will give us CCF. Okay, so we want to find this P. And similar, we can have also the problem for or OCF. We need both. Okay. Now how to do it? You can read the textbook. They explain how to find it step by step. But here I don't want to go over all those steps. I just give the result. We can have a kind of formula. By that formula, we can have this P. Okay, so we can work like this. How to find P? we need several steps. Firstly, we consider determinant Si minus A. Now we suppose this is Sn plus A1 s to the n minus 1 until An. Find this. Find okay. Find this one. Now if A is given, you can do the calculation, you can have this. Actually, what it is, this is the denominator of the transfer function. This is denominator of the transfer function. It is also called as a characteristic equation of the matrix A. Okay, so we find this polynomial here. Then let M is a matrix. M is a matrix. It will be okay. So here we should be 1. Here should be 1, and okay, yeah. Let me see. I have put it on the node. Okay. Yeah. This is just this one. Here's the coefficient. This coefficient is 1. The next coefficient is A1. Until we need n elements, so until A to the n minus 1. So this is the first row. The second row we will start by 0 and 1, and then you just put the element here. Okay. You copy the first row to second row, but shifted by 1 to the right side. So here's A1, and so on. Alright. Then you keep working like this. Finally, you have the whole matrix. This is M. And the second one, we need to find the C. Yeah, this is also C. I use a kind of a capital. This is what kind? Capital C. Okay, capital letter. This C equal to B, A times B, like this. Make this is n by n matrix. Here actually depending on the size of B and n by. If B is just one column, then you need n columns to be n by n, right? But maybe B is more columns, like B is 2 columns, 3 columns. That is the case. U is also a vector, so that means you have more than one input. You have several input, multiple input. Yeah, it also works. So you do this calculation, and finally you will pick the first n rows to make this is n by n size matrix, n by n matrix. All right. For example, if B has 2 columns, this is a B, and totally is a 5 by 5. Then you have A times B is here. You also have 2 columns, and then A squared times B. You have 2 columns. You pick these and drop this. Then you have these 5 rows. You use these 5 rows as C. Alright. This is C. Okay. We find what is C. You start from the matrix B and A. You do some calculation. You can have C. Now third one. Just let P equal to C times M. That's it. That's it. Then X equal to P X hat will give us the CCF. Alright. Yeah, we can do an example. Whatever. Suppose like we have a system, we have the matrix X dot equal to A. A is just 1, 2, 3, 4. Alright. Then X plus B. B is 1, 2. This is B. And Y equal to C times X. C is 1, 1 times x plus du. Suppose d is 1. Okay, just 1 times u, and we use this as an example. Okay, then you can have the CCF. Actually, you try to find the transfer function, then based on the transfer function you can have the CCF. But now we try to work in this way. Okay, because by this way we can know the new state variable, how to relate it with the original one. If you go to transfer function and then give the state equation based on the transfer function, you are lost the relation between x and x hat. Now if you want to hold this relation between x and x hat, you have to work like this way. Okay, so now we can work like this. We find this one firstly, the characteristic equation of the A. So we have the determinant of Si minus A. This is A. 1, 2, 3, 4 is A. So it's Si minus A. It will be the determinant of Si minus A. This is 1, right? The minus A S minus A is 4. Okay, this is the determinant. Determinant will be S minus 1 times S minus 4 minus 6. It is S squared minus 5S plus 4 minus 6. So it's minus 2. Okay, so we have M. It is, okay, you have 1 and the negative 2, negative 5. Okay, 1 and negative 5, you put in the first column, first row. The second row, you just shifted the first row to the right side. So 1 shifted to be here, and here you put a 0. Alright, negative 5 will shift outside the matrix, so we only need these two will be fine. Okay, this is M. And we also need a C. C is B and A times B. Right? B is one column. We want a square matrix, so we need one more column. Actually, this C, later we will use it, and I will explain why I use the C to represent this matrix. Okay, and this will be B is 1 and 2, A times B, So 1, 2, 1, 2, that is 1 and 4, that is 5. And 3, 4 and 1, 2, I have 3 and 8. 3 and 8 is 11. Okay, this is the C. Then we have P equal to C times L. C is 1, 5, 2, 11 times M is 1, negative 5, 0, 1. This is, just do some calculation. 1, 5, 1, 0, I get 1. And 1, 5, 1 and times negative 5, and 5 times 1. Okay, we cancel. 0. And the 2, 11, 1, 0. So it's a 2, right? 2 times 1, and 11 times 0. Then 2, negative 5, and 11. So I have negative 10 plus 11. Negative 10 plus 11. Okay, it is, right? Negative 10 plus 11. I have 1. Okay, this is P. Alright, now we have A. Okay, this is A will be canonical form, so I can put a C here. AC here. AC will be, we do the, is here, right? We use this as we perform the similarity transform. Then the new matrix will be this one, and this one, and this one. So okay, I just plug in. This will be P inverse times original A times P. This is the new A for CCF. Okay, P inverse is a 1, 0, 2 1s inverse times A. A is 1, 2, 3, 4. 1, 2, 3, 4. And P again. P is 1, 0, 2, 1. Okay, what it is? This is, we find the inverse matrix. Inverse matrix will be 1 over the determinant It is 1. Okay. And this element 2 by 2, we can work like this. We need to flip the location of these two numbers, but they are same, so just 1 and 1. And change the sign of this. So 0 is still 0, 2 will be -2. Okay, this is the inverse matrix. And these two, we times them together firstly. So 1, 2, 1, 2, I have 5. And 1, 2, 0, 1, I have 2. And 3, 4, 1, 2, I have 3 plus 8, that's 11. And 3, 4, 0, 1, I have 4. Okay, I think I have I have this 5 and 11, but I don't have 2, 4. Okay, I get these. Then I times these two matrices together. It is 1 over 2 times 1, 0 and 5, 11. So it is 5. And 1, 0 times 2, 4, I have 2. Okay, this is this is 1, not 2 here. 1 by 1, so nothing. 1 over 1, or 1 over 1 is just 1. Then, okay, which element? This one. -2, 1 times this column, I have -10 plus 11. And -2, 1 and 2, 4, so I have -4 and +4, it's 0. Okay, I have AC. It is the right way of the CCF. You can see what is CCF. I think I put something. CCF, where is it? CCF, SE. Okay. CCF, AC will be first row, some element. Then here's the unit matrix, here's a 0. Now is a first row is some element. Then here's a unit matrix, size 1, so just the one number. And here's a column of 0. Okay, so A is good, right? A is good. A is in CCF form. And the BC will be, we still use that formula. BC is here. BC will be negative, will be P inverse times B. Okay, so BC is P inverse times B. And the P inverse, we already have, this part is P inverse. So it is 1, 0, -2, 1. This is P inverse. And B is here, 1 and 2. So this is a 1 and 2. Okay, I time together. So 1, 0 times 1, 2, I get 1. And the -2, 1 times 1, 2, I have -2 plus +2. That's 0. Okay, BC is also good, right? BC is also is a good form in the CCF form. And then CC. This is C, but not that C, and also not this C. These two C are different. This small c means the controllable canonic form, and this large C is for this matrix. This one will be where is it? This one will be C times P, right? The new C will be C times P. C times P. It is C times P, and C is 1, 1, 1 and 1, and the P is this one, 1, 0, 2, 1. Okay, then let's multiply them. So 1, 1 times 1, 2, I get 3. And 1, 1 times 0, 1, I get 1. Okay, and D. DC will be just the D, that is 1. Right? This is D. D is 1. Right? D is 1. Nothing changed on D. So this is 1. Alright, so we have the CCF is x hat derivative equal to A. Now A is this AC is 5210 times x hat plus B. B, then we use a BC, that is a 10, times u, u is the input, and output y equal to c. Now c is this 3 and 1 times x hat plus u will be d times u. What's the d? D is here. D is 1 times u. The d is 1, so it's 1 times u. Okay, so this is CCF. This is CCF. And if you observe, you look at it, we can have the transfer function will be a fraction plus 1. The d is 1, right? So plus 1. Here the numerator will be as denominator will be s squared minus 5s plus 2 minus 2, right? Change the sign we need. And the denominator will be 3s plus 1. Alright, so we can have the transfer function looks like this. And we can also, this is the transfer function from, get it from here, right? We can also calculate it by the formula we just have. We check, double check, okay. Double check. Y over u will be c times si minus a inverse times b plus d. And c is, our equation is here. Okay, we have this one. C is 1 and 1. And then si minus a is 1, 2, 3, 4. And b is 1, 2. And d is 1. Okay, I want to check whether these two are same. Alright, 1 and 1, I keep it. And this one minus it, I have s minus 1, negative 2, negative 3, s minus 4. With the inverse times 1, 2, plus 1. Alright, then what is the inverse matrix? It is 1 over the determinant, which is s minus 1 times s minus 4, and minus negative 2 times negative 3, that is a positive 6. Okay, this is 1 over the determinant. And the matrix, I just keep it. The C, I just keep it. And this part, I need to move, flip these two elements. So this is s minus 4 and s minus 1. And change your sign on these two elements. So this is a positive 2 and a positive 3. Okay, so this denominator together with this matrix, that is the inverse of this one, and times 1 and 2 and plus 1. Okay, what it is? It is 1 over, this is a s squared minus 5s minus 2. And here I use 1, 1 times this. At 1, 1 times this two element, that is s minus 4 plus 3, so it's s minus 1. And 1, 1 times this is 2 plus s minus 1, so this is s plus 1. And here is 1, 2 plus 1. Alright, this is, okay, I write one more. Y over u, there will be s squared minus 5s minus 2. Here's this one times this 2, right? This 2 times this 2. So it is s minus 1 times 1 plus 2 times s plus 1. Plus 1. So this is, denominator is s squared minus 5s minus 2. And numerator is this part. I have 2s and 1s. I have 3s, and minus 1 plus 2 is plus 1. Okay, and plus 1. Alright, well done. And we double check. Are they same? We have two transfer functions. They are same, right? The first one is obtained directly from the CCF. When you have CCF, just observe it and pick the right element, right values from CCF, and put this value in the right place. You have transfer function. Right, like this 5 go to negative 5 here. This 2 go to negative 2 here. and this is 3. These 3 and 1, they go to 3 and 1. Okay. And the second equation is based on the formula. Which formula? With the formula is obtained by y over u equal to c times si minus a inverse b plus d. We use this formula. We use this formula. We can also have the transfer function. All right. So this is the CCF. And similar, we have OCF, right? For OCF. So another question. So for x dot equal to ax plus bu and y equal to cx plus du, we can find q. I use q for it. X equal to q times x hat give us the OCF. Give us the OCF of the system. So what is that q? Okay, we have similar method. Step 1, we need to find the c. No, not c. This is observe. It's OCF. So I use O, capital O. It is, I use c and c times a. C is a row vector, right? So the first row is c, and second row here is c times a. And put them together, I have O. But in general, we have more size, right? This is second size 2. That will be done. If you have more size, there will be c times a to the n minus 1. So this will be an n by n matrix, a square matrix. So let O equal to these. And M is same M. M is same M. Oh, M is the same M. It will be 1, A1 until AN, and 1, A1 until an minus 1, and here will be 1. This is 0. Where what are these AIs are coming from? They're coming from determinant of Si minus A, which equal to s to the n plus a1 s to the n minus 1 plus a2 s to the n minus 2 plus until the last one. Just put a, which one? 1, 2 to n, right? An. Okay. So m is still this m. Then step 3. Let Q equal to M with the transpose times. Okay, so which times which one? Maybe I need to put the M, not M in it. So that one is P is what? So we will reverse order. Oh, P is C times M. P is C times M. Okay. P is C times M. Now it should be M times O. Q is M times that O. This is O. This is Q. Right? Q has this part. O is just D. And with the inverse, let Q equal to this one. Then X equal to Q times X hat will give us a OCF. All right. We can try the same example. Okay. Just use same example. I still use this example continuously. Continue. M is the same M. but O is 1. O equal to C and C times A. Now we only need 2 by 2, right? So 2 rows will be fine. C is this 1 and 1. And C times A. So C times A. So 1, 1 times A. 1, 1 times 1, 3, I get 4. And 1, 1 times 2, 4, I get 6. Right? 1, 1, 2, 4 is 6. Okay, so this is O. This is O. And then Q will be M transpose times O with inverse. So M is, here's 1, then here will be A, but now I transpose, so A, that will be use same M, right? Same M. So I need to transpose, so this is -5 is here. So this is M with transpose, and times O. O is 1, 1, 4, 6, and inverse. Okay, what it is? 1, 0 times 1, 4, I get 1. 1, 0 times 1, 6, I get 1 again. -5, 1, and 1 and 4. So I have -5 plus 4 is -1. And -5, 1, here is 1 and 6. So I have -5 plus 6. -5 plus 6, this is inverse. This inverse equal to 1 over the determinant. There will be 1 times 1 minus -1. So it's 1 minus -1, and it's 2. And inside, I flip the location of these two elements, but they are same, so nothing changed. And change the sign of these two, which is -1 and 1. Okay, so this is Q. This is a Q. And also we have Q inverse in this part. Right? I remove this -1. I have the Q inverse, right? The Q inverse. So by the similarity, by the similarity transform x equal to q x hat, we have we say this is A, actually it's AO. There will be Q inverse AQ, right? Now it's a transform matrix Q. So what are these matrix? Q inverse is just this one, right? It's 1, 1, -1, 1. This is Q inverse. And A is 1, 2, 3, 4. And the Q is 1/2 times 1, -1, 1, 1. I put 1/2 in the front. Constant, right? Then this is 1/2 times, okay, the first two matrices I time together. 1, 1 times 1, 3, I get 4. 1, 1 times 2, 4, I get 6. -1 times -1 and 1, 3. I have -1 plus 3, that is 2. And then -1 times 2 plus 1 times 4, I have -2 plus 4. -2 plus 4 is also 2. And then 1, -1, 1, and 1. Okay, what it is? I copy 1 over 2. Then the matrix 4, 6 times 1 and 1, I have 10. 4, 6 times -1 and 1. So I have -4 and 6. That is 2. -4 plus 6. Okay, then 2, 2 and 1, 1, I have 4. And the 2, 2, -1 and 1. So it's -2 plus +2, that's 0. And let me plug in 1/2 inside matrix. There will be 5, 1, 2, 0. Is it good? Yes. Actually, this is a transpose of this, right? You just this is a CCF. This is CCF, right? CCF. You transpose, you have 5, 2, 1, 0, right? 5, 2, 1, 0. See, this one and this one, just a transpose. And also, we will see the new B will be 3, 1, and the new C will be 1, 0. Let me finish. The BO, there will be P inverse times B which is P inverse in this part, it is 1, 1, negative 1, 1, times B is 1, 2. Right? B is 1, 2. 1 and 2. So this is 1, 1 times 1, 2, I guess 3. Negative 1. I think I got something wrong. P inverse times B. I should have. No, sorry, it's a Q inverse. It'd be Q inverse. Q inverse, it is 1, 1, negative 1, and 1. So, okay, 1, 2, 1, 2. Yeah, it's 3, it's fine. Then negative 1 and 1, 2. It's negative 1 plus 2 is 3, 1. Is it good? Okay. Yeah, it's good. It's 3, 1, right? I guess 3, 1. And CO, there will be C times Q. C times Q. C is 1 and 1. C is 1. C is 1 and 1. Right? C is 1 and 1. And Q is half and this matrix. So it is 1, negative 1, 1 and 1, and a half. I put it in the front. This gives us 1 half times 1, 1, 1, 1, and 2. 1, 1, negative 1, 1, I get 0. So this is just 1 and 0. Okay, this is C. And D is just the same. D equal to still D, that is D is 1. Okay, so we have the OCF is x hat derivative equal to A is actually this is not x hat. X hat we already use it. I use x bar for it already. X bar derivative equal to the new A. New A is this one. It is a 5120 times x bar, and plus B, new B. B is 3, 1 times U, and y equal to the C. The new C is 1 and 0 times x bar, and plus D is still 1 times U. Yep, plus U. Okay. So we have OCF. Looks like this. Look like this. All right. Let me see. I finish this example. Okay. So that's all for today. And I will also post some homeworks after this class. All right. Okay. And that's all for today. See you next time. Bye bye.